Last time we reviewed a few concepts from Calculus 1. We discussed the definition of the derivative as a limit of average rates of change, so that the result is what we call an instantaneous rate of change. We looked at the derivative as the slope of the tangent line, and we did a visualization of the tangent line as a limit of secant lines. And then we discussed our collection of rules for finding derivatives and some of the derivatives for common functions. And then we moved on to a discussion of the definition of the Riemann integral and the fundamental theorem of calculus. The idea being that the definition of the Riemann integral, while it makes sense intuitively, is difficult to use to actually find areas under curves. And in that situation, the fundamental theorem of calculus is generally a much better tool. Today we look at a way of constructing antiderivatives. And the theorem that will do that for us is called the second fundamental theorem of calculus. So the first fundamental theorem tells us that if we can find an antiderivative for a function little f, in other words, a capital F whose derivative is little f, then the area under little f from a to b is found by evaluating its antiderivative at b and subtracting the value of the antiderivative at a. That's a very quick calculation, but of course it does require that we know an antiderivative for little f. Sometimes that's easier than others. And a lot of what we're going to do in the next couple of weeks is to develop some techniques for finding antiderivatives. So we'll discuss techniques like integration by parts, integration by substitution, integration by partial fractions. There are some others out there that we won't discuss. But those are all techniques we can use to find antiderivatives, just like we developed product rule, chain rule, and so on as techniques for finding derivatives. Today, though, we're going to focus on functions that don't necessarily have antiderivatives. And in that case, we can construct one based on the second fundamental theorem of calculus. So the idea is that if we have some continuous function, even if we can't find its antiderivative, we can define capital F as the integral of little f. So what we are saying is, if we have some function f of x and it's continuous, then a perfectly legitimate function would be to define capital F as the area under little f from some point a to x. So we define capital F in this way. We change the variable of integration from x to t here, and that's just to make sure we don't get confused between the value we're plugging into the function capital F and the variable of integration. So those should always be different. And nothing special about choosing t, just something that's different from x. And now the second fundamental theorem of calculus reports the news that if we construct f in that way, what we have done is make an antiderivative for little f. In other words, capital F prime, in fact, will be little f of x. So when we don't have an elementary antiderivative, one that's based on some known formula, then the second fundamental theorem is what we need to construct an antiderivative. So here's such a function. E to the minus t squared does not have an elementary antiderivative. There's no function whose derivative equals e to the minus t squared as far as the sorts of formulas we're used to thinking about. Graphically, here's what this function capital F represents. So this is the curve e to the minus x squared, and this is capital F. And remember, capital F is measuring area under little f. So for example, if I take the area under e to the minus x squared from 0 out to 1, that would be capital F of 1. We have plotted capital F of 1 here. And notice that the value of capital F of 1 is about 0.75 according to the graph. Now we would have to use some sort of numerical method or computer to calculate that area, but we certainly can. If we wanted F of 2, then we have to take the area further. We would go all the way out to 2. Looks like F of 2, it's going to be bigger than 0.75 because we added some area. And that looks like about 0.9 or so. So the second fundamental theorem says that if we define a function this way, what we've done is actually constructed an antiderivative for e to the minus x squared. So capital F prime is e to the minus x squared. Our second example is a common function that doesn't have an elementary antiderivative. And we have a similar graph here. So this curve is our function sine x divided by x. And notice that as sine does, this oscillates between positive values and negative values. So instead of capital F, this function is common enough that it has its own name. We call it the psi function, Si of x. And that's the black curve here, representing the area underneath sine x over x from 0 out to x. So I do want to point out a couple of things. One, notice that as long as the area for sine x over x stays positive, so that's out to about here, the graph for psi of x is increasing. So as we're adding area, positive area, the psi function increases. And notice that it starts to decrease right about there when the area turns negative. And the function will continue to decrease until about here. When the area turns positive again, psi of x will then start to increase. So once again, even though we can't find an antiderivative in the usual sense for sine x over x, the fundamental theorem says, in fact, psi prime is equal to sine x over x. So the second fundamental theorem can take a little getting used to. One thing that can be useful is to check it using a function whose antiderivative we can find in the usual way. So if we start with capital F of x, defined to be the integral of t cubed dt, then the second fundamental theorem says automatically we know that capital F prime is x cubed. So we can check this result when we actually can find an antiderivative for the function that's being integrated. In this case, we can because we're integrating t cubed. That allows us to actually apply the first fundamental theorem of calculus. And if we do, we see we can actually write down an explicit formula for capital F of x. So capital F of x turns out just to be x to the fourth over 4 minus 1/4. Well, now that we know capital F of x, we can find its derivative. We take the derivative of x to the fourth over 4. We get 4 times x cubed over 4 and then the derivative of the constant 1/4 is 0. So we end up exactly where the second fundamental theorem tells us we would end up, that f prime of x is equal to x cubed. And so what the second fundamental theorem is telling us is that even if we can't find the formula for capital F, even if we don't know it's x to the 4th over 4 minus a 4th, we do still know what the value of the derivative is. In this first example, we take a look at some straightforward derivatives using the second fundamental theorem. First up, let's say we define capital F of x as the integral from 1 to x of the cosine of t squared plus t dt. That's certainly not a function that would have an easy antiderivative, but using the second fundamental theorem of calculus, we know that the derivative of capital F must be the cosine of x squared plus x. Now note the lower limit never came into play. So this 1 doesn't affect the value of the derivative. If we had started at 10 instead of 1, the derivative of the function is still the same. Capital F prime is cosine of x squared plus x. What about something like g of x is equal to the integral minus 1 to x e to the t cubed dt. Well, once again, e to the t cubed is a function that would be difficult to find an antiderivative for. But the second fundamental theorem of calculus says we don't need to find that in order to know the derivative of g. G prime will just be e to the x cubed. So we'll see in the next example that things can be a little tricky when we combine a second fundamental theorem of calculus function with the chain rule. So for example, the kind of problem that we will face is something like we have the integral from 1 to x squared of some function like e to the minus t squared dt. And we want to know the derivative for that kind of function. And so notice that the difference is here, the upper limit is not x, it's instead x squared. And when we have a limit like that, we do have to be careful when we apply the chain rule, because that x squared acts as the inside function in the chain rule. Next, we take a look at how to apply the second fundamental theorem of calculus when one of the limits of integration isn't just x, but some other function of x, for example, like x squared. So we want to take the integral from 1 to x squared of e to the minus t squared dt and find its derivative. It's useful in these cases to think of this in a couple of steps. First, define capital F of x to just be the integral if we went from 1 to x. Now, we already know by the second fundamental theorem of calculus how to find the derivative for capital F. We know that that is just the integrand, e to the minus x squared. So that work will come in handy in a moment. Next is the observation that capital F of x squared is the integral that we have to deal with in this example. When we have to find the derivative of this integral, that's the same as finding the derivative of capital F of x squared. Now I think that makes it a little easier to see that we really do have the chain rule at work. So the derivative of the composition capital F of x squared is the derivative of the outside function evaluated at the inside times the derivative of the inside function. Here's where step 1 comes in handy, because we already took the trouble to find the derivative of the outside function. That's e to the minus x squared. So I get e to the minus x squared squared. We're having to plug in x squared. So we're taking capital F prime and plugging x squared in, where before we had an x. To finish this up, we have to multiply by the derivative of x squared, which we know to be 2x by the power rule. And so a final version would look something like e to the minus x to the fourth times 2x, or maybe just 2x e to the minus x to the fourth. Our last example shows us what to do if we have variable limits of integration in both the lower and the upper limit. Let's say we've got an integral now that runs from minus x squared to x squared of something like sine of t over t dt. And I want to find the derivative of that expression. Like before, I want to first note that the problem is based on the function psi of x, which goes from 0 to x sine of t over t dt. So I do know the derivative of that function by the second fundamental theorem of calculus. That is sine x over x. Next up, I want to write the integral minus x squared to x squared in terms of this psi function. So I am going to write this as psi of x squared minus psi of negative x squared. So now I need to take the derivative of that difference. Well, using the derivative of the difference is the difference of the derivatives. I have two chain rule problems to accomplish. Now these are both very much like the previous example. So derivative of the outside evaluated at the inside times the derivative of the inside, and I do that a second time, derivative of the psi function evaluated at minus x squared times the derivative of minus x squared. Now we already know the derivative of the psi function. That's right here. So in both of my chain rule derivatives below, we need to just plug in x squared into the derivative and then plug in minus x squared into the derivative. So my fourth and final step is that the derivative of the psi function evaluated at x squared is the sine of x squared over x squared. That's being multiplied by my 2x. Then I subtract off the sine of minus x squared over minus x squared all times minus 2x. Now I can do some simplifying because I've got so many minus signs around. Cancel those two. Since sine is an odd function, I can pull this minus sign out front and it'll cancel. And then I can cancel x's in both cases. Here, 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 here. So in the end, what I should get, sine of x squared over x times 2 plus sine of x squared over x times 2. And I guess since we can simplify that further, I end up with 4 of those sine x squareds over x, and that completes the problem. We can provide a proof of the second fundamental theorem of calculus that only takes one slide. We start off with the observation that the area under f of t from x to x plus h is bigger than if we take the smallest value for f of t. So over here, this notation min takes the smallest value for f of t for all t that are between x and x plus h. So we do that on the left, and on the right, this notation max of f of t takes the largest value for f of t on the interval from x to x plus h. Here's a picture of what's going on there. So here's my function f of t in red, and we are thinking about going from x to x plus h. And so the integral, right, is the area under the curve from x to x plus h. And this first inequality says that integral is going to be bigger than if I took the smallest value for f on the interval and multiplied by h. But it would be, the integral there would be smaller than if I took the largest value for f. So there's my max value. There's my min value for f on the interval x to x plus h. And so the integral then is sandwiched between these two rectangles. Next is the observation that the integral from x to x plus h is the same as f of x plus h minus capital F of x, because capital F of x plus h would be the integral from some point a to x plus h of little f. And we're subtracting off the integral from a to x of little f. So that's saying that if I come over to my picture, the area under the curve out to x plus h minus the area under the curve just out to x leaves me with the area under the curve from x to x plus h. So this value is in fact integral x plus h of f of t dt. Next, we divide everything by h. In this case, we're assuming that h is positive, so that doesn't change the direction of any of the inequalities. And then finally, we recognize that if the difference quotient here is stuck between the smallest value for little f and the largest value for little f, then it's also true in the limit. So if we take the limit as h goes to 0 on all three parts of the inequality, then we get something useful. On the far left, we're taking the limit as h goes to 0 of the smallest value for little f. We assume little f is a continuous function, so that has no choice but to be f of x. Similarly, if we take the limit of the maximum value on the interval x to x plus h and shrink that interval down as h goes to 0, then we also get little f of x. Stuck in the middle is our limit as h goes to 0 of the difference quotient. And that is the definition of the derivative of capital F. So our work has shown that capital F prime is stuck between little f of x and little f of x, and the only way that can happen is if capital F prime is in fact equal to little f of x. And that completes the proof. In our next presentation, we'll see the first method for constructing antiderivatives, and that's known as W substitution. See you next time.